Hello everyone, we are now presenting the research Taming the Variability of Soft Sensors. I'm Qiandi from National Taiwan University. And here's the outline for today. The first part is the introduction. As the fast development of HCI, researchers are looking for different ways to recognize gestures. For example, off-body sensors such as camera or IR sensors are commonly used. As for on-body sensors, you may have heard the EMG sensor. It measures the electrical signal of the muscle to influence the gesture. In our research, we found another way of on-body gesture recognition using a cool material called carbon polymer, or you can call it CP. So let me introduce the property of CP first. Rubber cores composed of carbon polymer are semi-elastic and also semiconductive. So when the cores are stretched by external force, the density of the molecules in the cores are changed, and thus changes the impedance. These two plots shows the characteristic of the CP cores. You can see here that the resistance values increase with stretching, and also you can find that the slopes are always larger at the beginning, which means that the material is sensitive to tiny stretches. So, with the characteristic of CP, we designed a wristband to use it for gesture recognition. There are three CP cores on a Ligua fabric. One is a full loop, which is sensor little, and the other a half loop. The wristband is then connected to an Arduino with a Bluetooth module and an ADC module for resistance measuring. So here is the circuit diagram. And here is the gesture set in this study. We hope to apply the recognition results in our daily life. So you can see that the gesture set can be directly matched to the control of a pair of earbuds, like we have up, down, open, which can also be matched to volume up, volume down, and play and pause. So in the preliminary study, we captured the resistance value of the three sensors and used random forest algorithm for inference. We did get good results in the same band and same user scenario. However, the result cannot be generalized to the cross-band or cross-user scenario. Here are the three main challenges. First is the hysteresis. We found that the resistance value after stretching depends heavily on the initial state of the sensor. This means that if the band is worn more tightly, the resistance value after performing the gesture may also be different. Or if we first perform a gesture with a larger resistance, for example, the down gesture, the resistance value of the next gesture may also be larger. The second challenge is the response time. After stretching or releasing, it takes time for the cores to recover to a steady state. This means that the one-shot measurement may not be good enough. The last challenge is the variation. Variation comes in many ways. For example, different wrist size should impact the initial value of the sensors. Or if the wristband slides a little on the wrist when performing gestures, the resistance value may also be different. So, to address these problems, we came up with some solutions. First is the floating point extraction algorithm. With this algorithm, we can capture the time series signal and use both the sensor values and the timestamps as features. In this case, we can solve the hysteresis problem and also make better use of the response time characteristic. The second one is the way of data collection. As mentioned in the last page, the resistance value of the last gesture may impact the resistance value of current gesture. We should ensure all gesture permutations are collected in the training data. The last one is the signal calibration. One of the biggest problems of the preliminary design is that it cannot be generalized to different users or different wristbands. With some efforts to normalize the sensor values and the timestamp, we can address the variation problem. So let me first introduce the floating point extraction algorithm. When users perform a gesture, there will be some distortion on their wrist muscle, and we can observe a peak on the resistance value signal. The purpose of this method is to extract the key moments from the signal peak. As you can see in the plot, we will extract 4 points on each peak, and we will mark them with the color order green, red, blue, and yellow. For each gesture peak, we will extract totally 24 features, including the sensor values and the timestamps for each floating point on 3 sensors. So the algorithm is composed of three parts: the best algorithm, point level majority vote, and a group level majority vote. In the best algorithm, we first filter the incoming signal with a sophisticated glare filter to make the signal much smoother. And after that, we find all possible floating points with a neat package in Python. The package function will find the most likely floating points within a small frame. The problem of this package is that if there is no real floating point in the frame, it will still find the most likely one, which might be a false one. To make better use of the package, we design an algorithm. We use the package function in a frame with a selected window size, and then we will shift the frame on the signal. And the frame can overlap with each other. As shifting, we also count the frequency of each floating point. If a point is chosen for more than a number of times, we will view it as a real floating point. After finding all possible floating points, we will remove the points that are too close since they are actually duplicate. Here is an example. The top left one is the original signal. After the filter, it will be smoother. The bottom one elaborates how we find possible floating points. In the first frame, we find the most likely floating point. Since there is no real floating point in this frame, it may return a false point like this one. After that, we shift the window to the second frame and choose another floating point. Now, these 2 points are both selected ones. In the third frame, point 2 is still the most likely floating point, so it is selected again. If we define the count threshold as 2, the count of this point has reached the threshold, so it will be taken as the real floating point. In the left plot, you can see that there are 2 yellow floating points that are very close. And they are actually the same point, so we will just keep the first one. Next, we will apply the point level majority vote. The purpose of this vote is to remove wrong floating points or recover lost floating points with the help from the other 2 sensors. For example, you can see here that we don't have the blue point on the green sensor, but after comparing with the other sensor, we can insert a point on the average of the other 2 blue points on the green sensor. Another example is that there is a yellow point near the red point in the orange sensor. After comparison, we will take it as a false alarm and then remove it. The last procedure is the group level majority vote. We first scan a single sensor. If the order of the floating point group on the sensor is not green, red, blue, yellow, we will discard this group. After the scan, we will compare the 3 sensors in the same rule as the point level majority vote. However, this time we will remove the false alarm points and recover the missing points in groups. The next part is the data collection. To address the hysteresis problem, we have to make sure all gesture permutations are collected. We have 3 gestures in our gesture set, so we will have 6 permutations. You may be wondering why only 6 instead of 12. You can see that the down-up permutation is also collected when we perform the up-down permutation for several times continuously. We conducted an IRB user study on 8 users. Each user was asked to perform 4 rounds of data collection. The first round will be taken as the training data, and the second will be taken as the same session testing data. After the second round, we asked the users to rewear the wristband. The data collected in this round is the cross-session testing data. In the final round, users are asked to wear another wristband with the same size, so that we can collect the cross-band testing data. Data from different users are taken as the cross-user testing data. Finally is the signal collaboration. The purpose of the timestamp normalization is to eliminate the impact of gesture lengths. You can imagine a gesture with length 1 second and another with 5 seconds. If the timestamps are not normalized, we cannot use the model trained with 1 second data to classify the 5 second data. We split the 4 floating points into 2 groups. The green and the red are group 1, the blue and the yellow are group 2. In each group, we normalize the range of sensor zeros timestamp to 0 and 1. An example is shown here. As for the resistance collaboration, We came up with two methods. The first one is the green point normalization. We would like to capture the value change within a gesture. To do so, we divide the value of the other floating points with the sensor value of the green point in that sensor. You can see an example here. All green points are scaled to 1, and the other points are scaled with the green point values. The other method is the max-min normalization. The idea is to scale the range of testing data to the range of training data, so that we can eliminate the absolute value difference between user-to-user or band-to-band runs. You can see the example here. We have signals from band 1 and band 2, with their max and min values marked as max 1, min 1, max 2, min 2. We have another point P1 on the first signal, and a point P2 on the same timestamp on the second signal. We can find a linear transformation to map max 2 to max 1 and min 2 to min 1. We then apply the same linear transformation to map P2 to another point P3 on the transformed signal. The main problem of this method is that a collaboration round is needed so as to find a linear transformation. A practical example is shown in this page. The left is the original testing data, and the middle one is the collaboration data, and the right one is the normalized testing data. You can see that the range is much closer to the collaboration data after normalization. The last plot is the evaluation. This plot shows the extraction rate of floating points after each stage in the algorithm. You can see that with the best algorithm, with only 30% of floating points are extracted. However, after the majority votes, we can find about 70% floating points. This page is to compare different collaboration methods. Without collaboration, you can see that the accuracy drops a lot on cross-band and cross-user datasets. However, with the collaboration, we are able to keep good accuracy even in cross-user scenario. The green point method works better in same session and cross-session, while the max-min method works better in cross-band and cross-user scenarios. So we will consider to leverage the strengths of both methods in our future work. The last evaluation is the feature importance. Since we have 24 features in our model, we would like to quantify and compare the influence of each feature. The idea is to randomly shuffle the values for one of the features, so we can view the difference between the performance of the model on the shuffled dataset and the original dataset as the importance of the shuffled feature. The testing dataset is normalized with the max-min method. You can see that we cannot hold high accuracy with only several sensors, so it is still best to keep the 24 features. That's all for my presentation. Feel free to ask if you have any questions. Thanks for your listening.